Okay, so we're now going to start looking at discriminants. These are going to be some invariants of our number fields, which will help us a lot in computing like integral basis for the rings of integers and so on. So let's start with a definition. So, definition 2.2.1. As usual, let K be a number field. And I'm going to let B be a set of B1 to Bn, a set of elements in K. So let that be a set of elements in K. Then the discriminant of B, of this set of elements, is defined as the following determinant. So you denote it by triangle B, delta B. This is defined to be the determinant of the following matrix. It's a matrix that you get by looking at the trace, in this case from K, always from K to Q, let's say. Here you do like B1 times B1, so the product of these two elements. And then all the way up to the trace, so now you do like B1 times Bn. And here you have the trace, K to Q, Bn, B1. So hopefully you can see the pattern. The trace from K to Q, Bn times Bn. Okay, so if I need this, I might just give the matrix a notation. I'm going to say this is the same determinant of TB, where TB is this matrix that I've just defined. So it's the traces of the elements in B. So this is just for some notation. Okay, so this is the determinant. This is the discriminant of B of a specific chosen basis. Let me give you an example of. Well, later on this B is going to be a basis. At the moment it's going to be any set of elements, but later on it's going to be a basis. So let's do an example of this calculation. So let's say this, take a simple field, a quadratic field, d square free, as usual. I'm going to let B be something like 1 in root d, easy elements. Then what is the discriminant of this set B? Well, just look at the definition. It's the determinant of the following matrix. So here I have the trace. I'll stop putting K to Q because in this case it'll just be easy. So it'll be a trace of 1 times 1. Here I have the trace of 1 times root d. Here I have the trace of root d times 1. And here we have the trace of root d times root d. What this is, well, this is the determinant of the following matrix. We have, if you work out what these traces are, you get 2, 0, 0, and 2d here. And what's the determinant of this matrix? Well, this is just 4 times d. So this is the discriminant of this set of elements. What is the use of having such a quantity, such a number attached? So clearly, if you notice, so delta B is going to be some number, and it's going to be some number living over where I'm taking a trace down to. So in this case, it's Q. So it's going to be some rational number because all of these entries are going to be rational numbers. It's a determinant of a rational matrix. So the entry that it's going to be a rational number. So what does this discriminant tell us? So one thing it tells us is it's given us a following proposition, portion 2.2.3, which says, again, let K be a number field. And again, B some set of elements, beyond Bn, set of elements of K. Then the discriminant of this set is not 0 if and only if the elements in B are linearly independent. In B are linearly independent. Here by linearly independent, I'm thinking of this as, let's say over Q, say, right? Thinking of this is a number field. This is a number field. I'm thinking of this as a number field over Q. So an extension of Q. So I'm thinking of this as a vector space over Q. So I'm talking about these elements. These are like vectors, and I'm saying that they're linearly independent over Q. And let's prove this. Proof. So let's start by just recalling some standard result from linear algebra, which you would have seen at least in some form, which is the following. So first recall the following linear algebra result, which is let's put that if V is a finite dimensional a vector space with basis say B1 comma some basis like this, and we have a bilinear form. A bilinear form on B. Then this bilinear form is non-degenerate if and only if there's the following determinant. So if I do V1, V1, Vn, V1, to the top, V1, Vn. So if the determinant of this matrix is different from 0. So this is a fact from linear algebra. And so this is maybe called, this matrix that's showing them here usually is called like the matrix associated to the pairing. In any case, we know something about the trace and the forms of pairing, a perfect pairing, and that's what we're going to use. So the now using this, so now by proposition, what was it? Proposition 1.7.8. We know that the trace pairing is perfect. So it's a perfect pairing. In particular, it's non-degenerate. So perfect pairings are always non-degenerate by definition. In particular, it is non-degenerate. Moreover, if you go back and look, this discriminant is a determinant of the matrix associated to this trace pairing. So what we saw was that the trace pairing, you could use a trace to form a pairing, right? And so, for example, my pairing of, I defined this thing, my pairing is just a trace to Q of alpha times beta. This is what I was using the trace to define a pairing like this. And so that this matrix that I've written up, let's see, up here, this is the matrix associated to the pairing, to the trace pairing. And then now this result from linear algebra says that if you look at the determinant of this thing, this is non-degenerate if and only if this determinant isn't 0. So we see that. B consists of linearly independent vectors if and only if the discriminant is different from 0. Great. So this is now relatively simple, but in a good way to check if you have some sets of elements which is linearly independent, which is great because when we're trying to find bases, one of the things we need to check is that they're linearly independent, the other one being that we have to span. So this is half the question sorted. But now let's just look at what happens when you change bases from one to the other. Like if you had two different bases, how does the discriminant change? So this is the end of the proof. Next, let's look at how changing B affects the discriminant. So here's a proposition. What's the number? 2.2.4. Let K be a number field. And I'm going to take B and B primed bases for K over, and these two things I want them to be bases for K over Q. Yeah, I think it was a vector space. Now, if P, big capital, this should be a capital P. I'll show why I chose P. Capital P denotes the change of base matrix, change of basis matrix. Then we have the following equality. It's going to be the same thing as the determinant of this matrix P squared times the discriminant of B primed. So if you have two different bases B and B primed, the discriminants differ by a factor of the determinant of the change of basis matrix squared. Okay, so this is how they're related, and let's prove this. So let's start using my notation. I'm gonna let TB denote, it's a matrix whose entries are traced from K to Q. I would say BI, BJ or IJ, BI and B. So this is the matrix associated to this trace pairing. So here again, we're just using linear algebra. So recall from linear algebra that if you have a matrix associated to the pairing, changing the basis changes the associated matrix by its conjugation. So that recall from linear algebra that if M is a matrix associated to a pairing like we have above, and we change bases, then M is conjugated by the change of base matrix. So in this, what does this mean in particular? So this means that we have the following, that the change of this matrix TB is just the same thing as B T transpose TB primed P. This is because we're just changing the basis of a matrix that's linear pairing. This is what I mean here by conjugated. So we have this. So now we just take determinants. And we get discriminant B, which is just, well, what do we get? We get discriminant of B, which is the same thing as a determinant T of B. This is the same thing as a determinant B transpose TB prime B transpose, but then now we just use, this is the same thing as a determinant of T transpose. Yeah. The discriminant of B primed times the determinant of P. And now a matrix and its transpose will both have the same determinant, and this is all commutative, so this now just becomes a determinant P squared times primed, and this finishes the proof. So again, this is just basically linear algebra about, if you have a pairing and then you change bases, how does the matrix associated to the pairing change? Let me just write, just using the, here I'm using that determinant of P transpose is the same as determinant of P. Just remember that. Great. So now, if we start trying to look to use these things, we're going to be able to say how our bases of like, say, the rings of integers will change, if they're going to be invariant or not, if they're going to change or not by some factors. How am I trying to say? If we have two different bases for our space for our number field, then the two different bases of a number field are going to differ by some square factor. And the fact that this thing is coming out as a square, if you have a square here, is going to be the important thing. But now let me start relating this to the bases that we're going to care about, which are the bases for the rings of integer. So note the following. This following results. Proposition 2.2.5 says let K be a number field. And assume that the elements that we have B aren't just any random elements in K, but assume that they're actually algebraic integers. And let B, say B1 to Bn, be elements of OK in this case. So they're all algebraic integers. Then then the discriminant of B is an integer. I'm not assuming that these BIs form a basis or not. I'm just saying that take any random set of elements. So this number could be 0, which would be fine if they're not independent. And the proof of this is really simple. Notice that if BI, BK, since the BI are in OK, then BI times BJ is also an element of OK, because this is a ring. Therefore, one of the properties we saw last time, or a couple lectures ago, was that the trace of an algebraic integer is always an integer. Therefore, the trace K to Q, so BI, BJ, this is in Z because, therefore, if you think of what we have a matrix of integers and we're taking the determinant. That's how we're getting the discriminant. And if you have a matrix with integer entry, then the determinant is again an integer. So therefore, the matrix TB has integer entries. And therefore its determinant is an integer. And this. And okay, yeah. Let me just give you so this is in the proof. Let me just give you a warning. So we're not. So this will maybe make sense later on, but just because you take a basis, if I were to take b1 and bn to be a basis of OK, consisting of algebraic integers, then it's not necessarily true that this basis is a basis for the ring of integers. So this is a bit confusing, but I'll put the warning here, and we'll come back to it and look at it, but and understand it some more. But just because finding a basis for K consisting of algebraic integers is not the same as finding an integral basis. So an integral basis means that we have a basis which gives us the ring of integers. Just because we have a basis consisting of rings of algebraic integers doesn't mean it's an integral basis. This is what I'm trying to say. And what I'll do next time in part 2 will be to start giving some lemmas which will tell us how to take some random basis of consisting of algebraic integers and slowly refine it until we actually end up with an integral basis. So I'll say next time, and we will see how to take basis of algebraic integers and refine it to make an integral basis. So you should, if this is confusing, maybe it'll be useful to go back and check what the definition of an integral basis was. So an integral basis is a basis consisting of algebraic integers, which is the basis for the ring of integers. So I want a basis of OK, not of K. Okay, so I'll stop here for now.